And welcome to the first substantive session. What we're going to be talking about today is reviewing regression. In our previous session, we discussed the idea of data generation and data generating models and the sort of conceptual issue that we try to model statistically. Today, we're going to be diving into the first component of a statistical analysis. And this really forms the starting point for an obvious reason, which is that multi-level modeling and all of the modeling techniques that we're going to be using, whether it's fixed effects or random effects or mixed fixed and random effects or structural equation modeling, all of them are regression-based modeling techniques. And so today we're going to go through the basics of regression, traditionally called OLS regression for ordinary squares, and we're going to try and start with the foundation. Now, this is not a complete review of regression. You took a whole course on this or a substantial chunk of a course going over regression. We're not covering all of the details. We're really hitting some highlights and some highlights that are particularly related to multi-level modeling and modeling with nested data structures. All right. So we are going to cover a few critical elements. First, we're going to discuss regression as a representation of a mean, conditional on some vector or group of x variables. So we have some set of x variables, and we want to calculate the mean of some dependent variable. We're going to call that y, and we can do that using regression just like we can using t-tests. So we're going to start with that. We're also going to begin to explore this concept of variance, and the whole class is really about how you chunk variance into components and then separately model those elements. That's what a random effect model is. The first model that we're going to learn in terms of a random effect model is called a variance components model because we're splitting the variance. And you already know some techniques for this. ANOVA is sort of the classic version of this and forms the foundation of the kinds of models that we're going to work with. So if you were taking this class in 1960, it would have been an ANOVA class, and that's how you would have modeled all of these nested features. You would have used ANOVA, which has some limitations, and we have much more appropriate, awesome, modern techniques to do that, and we're going to be exploring those. But these products are the child of ANOVA and come out of it. So we're going to go over ANOVA and the variance components in ANOVA models. We're going to talk about things like coding and interactions, which are pretty standard kinds of regression stuff that you have already worked on, and we're just going to review them. We're going to identify the random components of models that you already have worked with and thought about. You probably haven't thought about them as random components, but they are, and they are going to be the kinds of components that we are going to expand in the variance components models and then the other random effects models that we're going to use here. And then we're going to talk about regression, assumptions, assumption checking, transformation, those basic kinds of stuff. So all of this stuff should be a review and stuff that you've already had before, but we're going to try and start with a common foundation. And the reading for this material is the Sophia Reb-Hesketh book, Multi-Level Modeling, Multi-Level and Longitudinal Modeling Using Stata. It's a really comprehensive review. A lot of this is drawn from that, and so I think that if you read that and watch this lecture, you should start off with a pretty good idea of what we're going to be starting with in the class, a foundation. The real one important piece here is that we're going to go over some ways of notation and how we're going to notate various models, and it's a good starting place for that because that's a really important piece that you may not have fully integrated into your learning in your first regression course, but it's going to be essential for this course. All right. So let's start with a salient example, faculty salaries. So the data, again, comes from Multi-Level Modeling, the Sophia Reb-Hesketh book. And what we're going to do is we're going to start by modeling the mean salary of faculty. And then we're going to start exploring some of the ways we think that data gets generated. And we're going to do that by identifying variables that we think are related to faculty salary and testing some of those assumptions. And we're going to start with the simplest one, which is just a mean. So here you have the formula for a mean. It's probably a little different than you've seen it before, but it's the exact same formula. This symbol right here is the sum symbol, and it means we're just going to take all of the salary starting at 1 and going to the last one, which we'll call n, right? So that's what this I is down here for. So the first salary is 1, and let's say that's 10. The second salary is 2, and that would be 15. And the third salary is $40,000, right? So on and so on. So that's the first I. This is the second I. That's the third I. We're going to just add up all of those I's. That's what that symbol means. And then we're going to multiply by 1 over n, which is the same thing as dividing by n. So same way that you've always done and generated your means, you sum some variable, and then you divide it by the number of observations that went into that sum. And so we're going to start by estimating that. I use the sum command, and then I use this comma and then D, which gives me details. D stands for details. So if we just said sum salary, and that would give me the mean and the standard deviation and the range. But it wouldn't give me all of this other detail. Like here, I get the median, the skewedness, the variance, the kurtosis, and I get a sense of how what the smallest values are, what the largest values are, and then what my 75 and 25% intervals are. So I get a really good sense of what my data is, and it's always very important to understand your data clearly. So one thing I've done with this data, and I should make this clear at this point, my puppy dog, where'd that go? There we go. So in Stata, I have a do file, which is what you see here, and then the Stata window, which is what you see here. There's other things I can get on the Stata window, but I'm just going to do this for screen real estate size stuff right here. So I'm going to calculate the salary, which is in raw dollars, in $10,000 units. And I'm doing that because I just want the scale to be different, mostly for the variance on the ANOVA part that you'll see in a second. So I can run this in Stata, and I get that same output that you just saw on the slide. So we have our basic understanding of salary. The mean salary is $50,000. And then there's quite a bit of variability around that. So the average variability is around $12,000. So there's quite a range. You'll notice that there's a bunch of people chunked up here at the bottom, and those are, and you can see like there's a lot of people at the bottom. 10% are in the 30 to 40,000 range. Then you hit 50 at the 50%, and then there's a tail, and you'll see that when we look at the histogram as well. So the histogram tells that story, right? So there's sort of a flat edge. Nobody's making less than this. There's a floor to what the values are, but there's not quite the ceiling, and this tail goes off like that. And you see this a lot with dollars because there's a few people that make a lot of money. Most people are clustered toward the lower and lower middle. So this is a very typical kind of thing that we're going to see. And then when we get to the end and we start talking about residuals and dealing with the residuals, there's the idea that we have to deal with this in some way in order to make our residuals normal, and we'll talk about that as we move through. But we probably aren't that interested just in the idea of salary. We are probably interested in explaining what causes people to have higher or lower salaries. And one thing we might be interested in, and we certainly are here in the School of Social Work, interested in gender differences in salaries between faculty that are doing equivalent kinds of work. So we're going to try and figure out, first, are there differences in mean salary between men and women? And then we're going to explore some of the reasons why there might be differences in the data set that we have. So the first thing we're going to start with is a mean model, and this top model you see here is a restatement of the mean model that we identified before, but we're saying there's something that we think is related to Y, and that is X, in this case, gender. And so what we're going to do is we're going to calculate two different means. We're going to calculate a mean for I equals 0 and I equals 1. In this context, I equal 1 is going to be male, and I equals 0 is going to be female. We're also going to calculate two different variances. Because we're going to calculate two means, we're going to get two variances associated with that as well. And again, that's denoted by the I here. The I will be 1 for male and 0 for female. All right, so we can express that. There's an arrow right here. We can express that in these two equations right here. Y conditioned on x equals 1 is going to be normally distributed with a mean and a variance. Y conditioned on x equals 0 is normally distributed with a mean and a variance. So all we've done is taken the mean, that $50,000 a year salary mean, and we've said, okay, we're going to calculate one for men and one for women. That's all we're doing with this formula. Now, we run Stata, and here I think I ran, I think I did it in, I think I did mean. Nope, I did some, but I also had this nice little, there's this nice little feature that if you want to do a command like sum for a group, you can do it with by sort here. And by sort allows me to get the separate means for men and for women, and that is a command that we will use a lot in this class, by sort. So this, I didn't put the comma D because I didn't want all of the details for this. I just really wanted to show you that women, which is 0 in this context, have a mean salary of 43,000. Men have a mean salary of 53,000. So it turns out that men do make more than women in this data set. And so we're onto something, right? There's evidence. If you look at these standard deviations, it certainly looks like this difference is going to be a meaningful difference. Certainly, I would take a $10,000 difference as something that's meaningful, regardless of its statistical significance. So if we're likely to have a difference of $10,000, we're onto something here. We might want to reformulate this rather than just calculating a mean for one group and a mean for the other group as a regression model. And we have not changed the model at all. These are the exact same models with one small difference. You'll notice here in this model, we have a variance for men and a variance for women. Here, we're just going to have one variance, and it's that term. We'll talk about that in a second. But here we have the intercept, which is the grand mean. In our case, it's going to be the mean of the female mean salary, and then here's going to be the male coefficient. So x is going to be 1 when it's men and 0 when it's women. So if it's 0, then a number multiplied by 0, it doesn't matter what this number is, that's going to be 0, right? And so that's why this represents the mean salary for females, and then this will be the difference between the salary for females and the salary for men. All right, so now in this regression model, we've added a static process because we know that there's variability. We're not going to have a single point that represents men and women, and that variability is what we're really interested in. So we need to have some way of formulating it, and how we're going to formulate that is with this error term. And we're going to say the error conditioned on the x's, so we're taking account of all of this stuff right here. These errors are going to be normally distributed with a mean 0 and a single variance. So we've just got one variance term that we're going to estimate here. And this is the assumption that you've been familiar with. It's the assumption that you used in your introductory regression classes. And here we've estimated the regression model, and we see the same thing. You'll notice that this is the exact same mean that we got before for women in terms of their salary. This is the exact difference that we got before. This is the exact same model that we ran before when we calculated the mean for women and the mean for men and just looked at them and compared them. Here we get some additional features, and this is why we use this thing. We get a t-test here, and that is highly significant, confirming our intuition that this $10,000 difference between male and female salaries is something that you wouldn't get by just random chance alone. So there's compelling evidence that there's something going on with gender and salary, which should surprise no one at this point. All right. So to sum up what we've done, and this is a feature this is something that you'll learn about me, is I love my graphs. You should love graphs too. And you should invest time and energy in learning how to graph. Now, this graph, for example, one of the reasons why I always give you code is because you can do it yourself. So here's the graph. It's an example of what it is. I'm not going to walk through what all of this means. A lot of this is just doing the text stuff, but you can estimate this in Stata, and you get the same graph that I saved as output and put into the slides. My puppy dog again. Okay, so Here's the male mean, right? So here's all of the men. This blue line represents the male mean. These are all the women, right? At 0, men at 1. And so this red line represents all the women. And here you see the regression slope. So in a regression, when we have a dichotomous variable with just a 0 and a 1, the slope is the same as estimating the difference between the means of the groups. So again, everything we've done is we've just done one thing so far. We've just done it in 2 different ways. We could have also run a t-test and we would have gotten the same t-value incidentally. So the graph shows you the relationship between the line and the means. And we're gonna spend a lot of time in this class looking at graphs and images to sort of get an intuitive sense of what's going on with our data. But I hope that this conveys the sense that with a lot of regression, we're really just doing mean comparisons. We're just doing means accounting for a whole host of other variables. In this context, we don't have any other variables. We just have gender. If we were to add other variables, we would still be doing the same thing, but conditioning on those other variables. When I say conditioning on, mostly I mean setting to 0. And we're going to talk about that in the context of centering because that makes, for example, the intercept more meaningful. And we'll talk about that in the next example. But the idea here is that we're just making comparisons. And one should be cautious when using comparisons to make causal inferences because we don't know what the cause of this is. There could be a whole bunch of things that explain why gender is associated with differences in salary. And we're going to explore some of them, but it's likely that we don't have, certainly with a cross-sectional data set that we have here, it's very unlikely that we would be able to estimate the complete data generating model that produces salaries. There's a whole bunch of stuff that's just not measurable. There's a whole bunch of stuff that's very subjective and idiosyncratic between different schools. There's a whole bunch of stuff that's subjective and idiosyncratic between people. And it's very hard to get the full data generating model. All models are wrong. As I've said before, some models are useful, and that's where we're going to try to get to. But making sure that you graph your images is one important piece in helping you understand your data and understanding what these comparisons, not causal explanations, but comparisons mean. So as I mentioned before, when we estimated the 2 separate means, we estimated 2 separate variances. And sometimes that matters, sometimes that doesn't. In the context of what we're doing here, it probably isn't, there's probably not enough variability or difference between the 2 variances to have something that's really important for us. But one critical assumption of the most of the models we're going to run, and we will talk we'll talk at some points in the future about how you loosen this assumption, because you can model these differences. You can add coefficients, and there are ways to deal with this. But for now, our regression model assumes that there is equal variance across the line, and so that's encapsulated here because there's only one variance term. We're just going to estimate a single variance. So we're assuming that the variance at this place along the xy axis, xy coordinate system, is the same as this, is the same as this. This is the heteroscedasticity assumption. So we want homeoscedasticity, same variance, as opposed to heteroscedasticity, different variance. Now, we can use robust standard errors. There's ways to deal with that. Bootstrapping, there's a whole bunch of methods that we can use to adjust for that. So it's not the biggest deal in the world, but it is a critical assumption that we need to just keep in mind as we think about our variables and think about the relationship of our variables between each other as we make assumptions. So moving on. Here we have a third way of looking at this same set of data. So we've done 2 means. We could have done a t-test on that. We've done regression, and now we're going to do ANOVA. ANOVA is a precursor to multi-level modeling. It is the old grandfather or grandmother of multi-level modeling. If you were taking this class in the 60s, we would have been learning about ANOVA, not about multi-level models. There's a whole bunch of reasons why we don't use ANOVAs very much anymore, and multi-level models are a much much better way of dealing with these issues, and much more flexible. But in the context of the example here, where we have a continuous outcome variable and a categorical or a factor predictor, it works reasonably well. It doesn't work if we're trying to predict a continuous variable with other continuous variables, then we'd run out of degrees of freedom very quickly. But here it works. And I want to point out, this is, again, totally equivalent to the OLS regression that we just ran, the ordinary least squares regression that we just ran. So we're just seeing the same thing over and over and over again. But ANOVA gives us a focus on something else that you also get in your regression output, but is going to be very important for the work that we do in this class, which is we are going to try to understand the pieces of variance. We're going to break the variance of our dependent variable conditioned on our x variables in a lot of different ways. That's what random effects models are. The first model that we're going to learn is called variance components models because we are breaking out the variance components. It's the simplest random effects model. So to understand these differences, we can look at how much variance gender as our model captures of total salaries. So when we do ANOVA, we break it into three primary components. There's the total variability. That's all the variability in the data, and that's just that first mean that we ran, where we calculated the mean of salaries, and we calculated the standard deviation or the variance. That's the variance I'm talking about. That's the total variability in our data, the variability around the grand mean. We're going to then take that, and we're going to take the second piece that we did, where we broke those means into two separate means, and we're going to say, okay, so there's some variability that's in that model, in that breaking it into two means. And then within those two means, there's still a bunch of variability left. Men didn't have the same salary and women didn't all have the same salary. There was still variability within groups. So we have the model, which is the between groups, between gender variability. And that's represented by the difference between the mean of men and the grand mean, and the mean of women and the grand mean. And that's that variability. And then within those groups, the difference between all of the men and the men mean and all of the women and the women mean represent the remainder of the variance, the sum of squares error, or the residual. We can look at this in terms of formulas. So as I just described, if we take all the observations and subtract them from the mean, square them, and sum them, we get the variability. So that's the variance, right? That's the variance that we saw in that first model. When we created two separate means, a mean for men and a mean for women, we created this variable right here, right? So that's the estimated mean. That this is the top for estimation. So we estimated a mean for men and a mean for women. We subtract that from the grand mean, and that's the amount of variability that the model has captured. But within our mean for men and our mean for women, we still have some variability between the individual observations and those means, and that's the remaining unexplained variance. So we've just taken this total variance and we've said, all right, we're going to take the part explained by gender. We'll take that out. That's represented by the mean for men and the mean for women as different from the grand mean. So that's the information provided by gender. And then all of the remaining variance, we're going to call the sum of squares error, residual, that kind of stuff. All right. So we can look at it, and so that's the formula way to look at it. We could also just look at a picture, which I find also compelling, as you know. So this is the mean for men. This difference right here, that is the model variance, right? So that's represented by the model sum of squares. The variability within men, so this is the variability between genders, right? So this is our between group variation. So that's the difference between men, and here's the women line right here, right? But then within men, there's still a bunch of variance, and that's the variability between each of the individual observations and the mean for men. And women have the same thing. There's variability between each of these observations and the mean for women. And that is the remainder, or the sum of squares error. The mean sum of squares, the model sum of squares plus the sum of squares error equals the total variance, the total sum of squares. So we've got the total, and then we've broken the total into a model-based component and then the remainder. We can see this in the output. So when we run stata, we calculate when we run the ANOVA command. Notice the nice little I there. We'll talk about that in a second. We have the model and male are exactly the same because we only have one variable in the model, male. So male and model are exactly the same thing. This is the variability attributed to male. This is the residual variance. So that's attributable to all of the within group variability between the gender, all the individuals within their gender group, and the mean of that gender group. When we can get this F-test here, which is classically how we look at ANOVAs and determine whether the model is statistically significant. We do that simply by taking the mean squared error terms for the model and for the residual. And the way you get this is by dividing this number by the degrees of freedom. The degrees of freedom, you'll notice that there are 514 individuals. We do some adjusting, so we take some out. Plus, we take one out for the model here because we have one variable in the model. And so then there's another free one that we take out to adjust. So because we calculated a mean. So we divide this number by this number, that equals this number. And then this number, then the model variability divided by the residual variability adjusted for degrees of freedom gives us the F-test. That is a highly statistically significant value. You'll notice those are exactly the same. And if you pull out your calculator, you'll see that it's a little off because these numbers, I didn't put in all the numbers. I rounded them like that. The other thing to note about this is that this number right here is our error variance. It turns out to be the square root of that. So you just take the square root of that and you get that. All right, so that's what the pieces of ANOVA are. Again, the key thing here is that we have three portions of variance. We have the total variance, which is all the variability, and that's just your standard variance. We have the model variance, how much the model captures. And then we have the remainder, the residual variance. So those three pieces. Now, you've used a lot of this because this is basically what the R squared is. So R squared is the proportion of variance captured by the model over the total variance. That's exactly what your R squared is. And you've interpreted these before as a proportion of reduction in error, knowing the x's, or how well x predicts y, however you want to phrase this. Mathematically, it's the proportion of variance attributable to the model over the total amount of variance. So how much of the variance is captured by the model? All right. So this looks very similar to the image that we saw earlier. But you'll notice x here is no longer just a 0 and a 1. We have a number of values of x that can be found in our data. And so we've lost the ability to do this simple 1, 0. Like if you wanted to calculate a mean for everything here and everything here and everything here, you could theoretically group these like that and do that, but that would be crazy because you would lose a whole bunch of your variability and you'd sort of, you'd end up just doing the average of these. Why lose the data when we have modern computing and techniques? And that's why we use regression as opposed to ANOVA or other things. So let's move to regression. Now, one of the other benefits of regression is we can begin to add other variables. We know that gender is related to salary, but are there other things? So one hypothesis might be that men and women choose different professions. So some professions, so there's the more liberal arts professions like philosophy or English or history or German or something like that, are going to command a lower salary because for a variety of reasons, but one of which is there's not market competition for them. There's not a whole bunch of people in industry trying to find scholars of, early Roman Republic. So if women choose disciplines that have less market command, they're likely to have lower salaries, not because of gender, but because of their affinity or proclivity or being pushed into, or whatever the explanation is, into different salaries that have, into different market segments, in other words, academic disciplines that have different market value. And so here there's a variable called market. If we look at the variable called market, we can see here that the variable actually has a mean of 1. The 1 is the average discipline salary, and then the proportion of above or below that is what. So it goes from 0.73, 0.71 to 1.33, and it's pretty low standard deviation. So there's a pretty narrow range of salaries. The largest discipline in this context would be 1.3 times the average. The lowest would be 0.71 times the average. So it's a relatively small range of salaries, but I want 0 to be meaningful here, and 0.92 or 0.94, I guess this is the average. This is the mean here. This is the median. 0.94 is not really that meaningful, and there's no zeros, right? I want 0 to be meaningful, so I'm going to center it. And the way I do that is I use this egen command here, and I say, I create a new variable called mean market, and then so egen mean market, that's a variable name that I created. Mean is a stata command. Bracket market is the name of my other variable. I do that. I get the mean market variable, but I'm not done yet. I have to take the individual's observations market value and subtract it from the mean market. Now, if we look at the data here, we don't need all this stuff. If we look at the data here, you'll see there's only one value for mean market. That's the mean of market, right? That's what we just saw, that number right here, right? So all I did is turn that into a variable, and now I'm going to subtract the market variable, which does differ across people. I'm going to subtract that from that, and then that centers the market variable at the mean market. So it doesn't do anything to the size of the coefficient or any of that element. All it does is allow me to have a meaningful 0 that I can then use when I interpret things. So here we go. Let me add that in there just for consistency's sake. So we run it. We get the model. This is the same model that we just saw there. You'll notice that you can get the sum of squares stuff here. So this is the ANOVA output that we talked about before that shows up in our regression. And here we have male. So male has a lower coefficient. There's less of a difference between men and women. Some of the difference between men and women, it turns out, are explained by different choices of different disciplines that men and women go into. So math, sciences paid higher than liberal arts. I would guess that would be, not knowing the data in detail, my guess would be that would be the explanation here. And it turns out that both male and gender and the market condition are statistically significant. Now note the scale of the variable here. There's a problem with the scale of the variable because there's no. Let me take a step back. Let's interpret these coefficients. So for male, as we move from female to male, which is a 1 unit difference, right? Because female is 0, male is 1. A 1 unit difference moving from female to male is associated with about an $8,700 difference in salary. So on average, for the average market discipline, the difference for men and women is $8,700. Again, a woman at the average market condition makes 43. Now, you notice how I said average market condition? You know why I can say that? Because I just centered the variable. Otherwise, it would have been when the market condition is at 0, and there's actually nothing close to 0. The lowest value is 0.71. So that's out of scale of the variable. So when we talk about the linearity assumptions, your data has a range, and you want to make your coefficients meaningful because that's where you have your information. And so that's why I centered this, because now I can say at the average market condition, a female salary is $44,000. A male salary is going to be $8,700 more than that at the average market condition. Now, as we move from 0 to 1, then we get a $30,000 difference, but there's no salary range that large, right? So the largest difference, if we go here and we look at let's do sum, right? The largest difference is from negative 0.21 to 3.8. So there's not even a full point difference here. So if we wanted to understand what's the difference between the average market salary and the highest market salary, we can calculate that. 2.99 was the coefficient, right? And we're going to multiply it by an x value, in this case 0.38, which is the highest x value, right? So that would be $11,000 difference. So the difference between the average person at the average market condition and a person at the highest available market condition is not this value, because that's a 1 unit change, and we don't have a 1 unit change. It's a $1,100 change. So that tells us something about the scale of it. Now we could change the scale. We could add, so for example, we could multiply that market condition, that centered market variable, by 10 or something like that to change the scale, and make it meaningful in some way. I don't know how meaningful it is in this context anyways, but that's how one would interpret the market conditions' effect on salary. So looking at this from a graph point of view, we are on the x-axis down here, we have market condition. We've centered it at 0, right? So this is where our coefficient is. We have our salary variable. Notice that the salary, we don't have any salaries too low, right? The bottom salary was around $30,000. So in this context, 3. So we've got a line here for males, a line for females. The difference between these two lines, that's our beta 2, that's our male coefficient. The slope of these lines, that's our beta 3, that's the effect of the market value for a discipline on salary. So we've taken our basic mean model, we've expanded it. We still are calculating the mean difference for men and women, but now we're making another statement. This model is the mean difference for men and women at the average market condition. So we're more specific in our comparison, and this is what regression allows us to do, is develop more specific mean models. So switching topics. We've coded male as 1 and 0, and that's a very standard, sometimes we call it dummy coding, or I'm going to call it here standard contrast coding, where we have a reference group. In this case, female is our reference group because that was the one represented by 0. And then we have a set of, or in this case 1, but theoretically we could have a set of other variables that would be not 0. And so we can compare the baseline to those others. Now, if we had a bunch, so like race is the classic example of this. So if we have white and we want to have white as the baseline, right, we would not include white in the model, and we would have a coefficient for black that would be 1 or 0, a coefficient for Asian that would be 1 or 0. If they're Asian, they're 1. If they're not Asian, they're 0. And then because we leave white off, they would be 0 for everything. So the white value would be pushed into the intercept, and then the black coefficient would represent the difference between black folks and white folks. The Asian coefficient would represent the difference between Asian folks and white folks. So that's a standard kind of categorization and coding that you've used. In Stata, as I pointed out before, we don't have to create all of those dummy variables. And in general, I don't like creating all those dummy variables because I don't like having a proliferation of variables in my data set. And there's some nice features when you use, in this case, I dot and then the var name, and that gives you that contrast coding. And you saw that I did that when I used regression or ANOVA and the male variable. The reference group can be changed. So if you have if you have a variable called race and you want to switch, so like let's say black is 1, Asian, or let's say Asian is 1, black is 2, and white is 3 because you went alphabetically, and you don't want Asian to be the baseline, you want white to be the baseline, you would call that IB3 because white in this context was 3. So I base 3. And so you can do it for anything. You can change the reference group. Now, just changing the reference group keeps the coding and the coding the same, right? So you're still contrast coding. You're still using 1 as the baseline, and then all of the other coefficients are compared to that. Now, if we want to center white a lot, which we apparently do because that's how we code most of this, that's fine. I think that there are better ways. There's a whole bunch of alternative coding schemes, and I think people should be more considerate of what coding scheme they choose. The Stata manual has a really good description of these, and I put a link there. The UCLA website, the stats website, if you're not familiar with it, you should be. They have an example of this, and that's where I got this table from. So we're going to do a difference coding, a forward difference coding example in just a second, but there's a whole bunch of ones. One I use a lot are deviation codings, which compares to the grand mean. So for example, with race, I like doing it to the grand mean. So I say, okay, the mean of all of the variables, and how does each of them differ from that? And there's all sorts of fancy things you can do, like you can do weighted mean comparison. So, if I have a data set and it has 1,000 white people, 800 African Americans, and 5 Asian folks, those 5 Asian folks don't contribute much to the overall mean. So it doesn't tell me much to look at the mean difference for them. So I can do a weighted mean comparison where each group's mean is averaged, and that allows me to see sort of the differences with a weighted mean. So there's a variety of different things you can do. Orthogonal polynomial contrasts and helmet contrasts and a whole bunch of other things. But let's do an example with forward difference coding, and I think it will illustrate the point quite nicely. So there's another variable in our data set called rank, which one might assume, and I think correctly, that salary is associated with rank. So assistant professors make less than associate professors, who make less than full professors. Now, if I use the standard coding, what I would get is, let's say a full was the baseline, I would get the difference between associate and full and assistant and full, which is not really the comparison I'm interested in. What I'm really interested in are assistants paid less than associates, and our associates paid less than full. And that's the forward difference coding. So I'm moving, if I have some ordered variable and I want to look, does step 1 differ from step 2, and does the step 2 differ from step 3, then I can use forward difference coding. Now, if you go to the UCLA website, you'll see the code here. I didn't create this myself. I in fact, when I want to do this, I actually go to that website and I calculated it. I'll show you another way in a second that I actually do it. But you can see here that it's not that hard. You take, so this is the associate professor, and that gets 2/3 of a value. The other two get minus 1/3 of a value. And if you work this out mathematically, you can see why this works. But what it ends up doing is comparing 1 to 2, and then 2 to 3. So you get the values here, which is this is the output from the regression. And you'll notice that this number, 72, is the difference here. And then you'll notice this value 13 is the difference here. So I'm able to calculate these differences and create a statistical test for these differences. Now, how I actually do it is I use the margin commands, and I'll show you over here. Right, so here's the coding that I just did and I showed you, right? We can run it, get those values. I then just regress and use x1 and x2, which are the variables that I used for the contrasts. This is the first contrast, that's the second contrast. I just showed you that. It is, I would run regress with salary, I.rank. So I'm regressing salary on rank. I use the I.rank here for a reason. When I do that, I get the standard coding. So this is associate versus versus assistant. And you see that, right? So these are the same numbers there. And then I get full versus assistant, which is not what I want, right? I want to know whether full is different from associate, because I want to know, does each step in the rank increase produce a meaningful difference in salary? And so to do that, I can use the margins command, which is a really helpful tool for understanding interactions and a whole bunch of things. And you'll notice that these values are the exact same values that I got when I did the coding manually. So you can use manual coding, you can use the margins command. It gets you to the same thing. I think the point here is that you should think about how you do your coding, because you sometimes want different things, and there's lots of different options. Don't be stuck with just the standard. All right, interactions. So does the salary for men and women stay the same over years of experience? Is it just an additive function? Is it just that, men start at higher salaries and then as they move through, they retain those higher salaries? Or is there some relationship between years of experience and salary? So we have a history of gender discrimination in our country. So often the older faculty, which would be of higher rank and have more tenure, I don't mean that in the literal tenure, I mean that sort of the time tenure. Those people would be paid more than people that just started. So maybe what we're seeing is that difference. Maybe what we're seeing is some other function that, men are more schmoozy and so they are able to pay more. Society's biased toward men. There's a whole host of ways in which men might have a higher slope over time than women. But that would be a multiplicative model, not an additive model. And all we've run so far is additive models. So if we've got a model in which men and women and the differences between their salaries stay parallel, as those lines demonstrated earlier, then we're good. But if not, we have to deal with it as an interaction. So here we have the interaction model. I'll show you how I did that in Stata. So the first thing I did is I took male and then years since degree. That's the years degree variable. And I generate a new variable describing the interaction called male years, right? So that's just multiplying these two together. And then I run a regression with salary, male, market condition, which we're not really going to look at here, years since degree. So both male and years since degree are in it. And then the interaction term, which multiplies males and year together. So for females, this variable is 0, this variable is 0, and all you get are these two variables. So the intercept is going to be the average female, the average female salary at the average market condition and right after she got her degree. Then if we add male to that, and we start at 0, right? So the average male, this coefficient is going to represent the male at the average market condition at 0 years of experience. But then this variable, years of experience, is going to tell us how much it increases, and this variable is going to tell us how much it increases above the female increase. So let's look at the interaction. All right, so as we just said, I've shifted back to salary here, so this is just raw salary numbers. So the average female, right in the average discipline, right after, so years since degree is 0, right? So she just got her degree. Her salary, her expected salary is $36,000. Each year, she's expected to make $700 more. All right. Here it looks like male is negative, but it's not statistically significant from 0. There's a lot of noise. Adding a regression, adding an interaction term does that often because it messes with the slope. And there's not a lot of people that just got their degree and just got hired, right? So most people there's not a lot of data there, so it's not a stable estimate. But so suffice it to say that the male at the average market condition and at 0 is probably making somewhere around this as well. So, but for men, each additional year, they get their $763 raise, but they get an additional, above women, $227 raise. So they're getting about $1,000 more, whereas women are making about $760 more. You'll notice that this is statistically significant. There's quite a wide range there, so there's a lot of variability, and it's not a particularly stable estimate, and you often get that with interaction effects. But we can see this in the image here. So remember in the previous model, these lines between men and women were, I'm sorry, that I'm not very good with these mouse drawing lines, right? Men and women, were parallel all the way through. Now, they're not parallel. The longer you go on, the bigger the gender difference is. So the gender difference is really narrow at the beginning, but then grows over time. That's what the data suggests. So interactions are a very useful tool for understanding nonlinearity. Now, let's talk about some other regression issues. Collinearity. So collinearity are when two or more predictors are highly correlated. And because, as I mentioned, we're partially out the variance, right? So if they share the same amount of variance, and correlation is just shared variance. How much of the variance between two variables is the same? If you look at the formula for correlation, it's just the variance of one variable over the variance of the other variable with some other stuff in there. But if the variance is the same, if they each explain the same variance, then it's hard to separate them because they're not really separated. Now, most of the time, this is not that big of a problem. It's also easy to check, but you should make sure your variables aren't the same. That's sort of a basic thing. You should understand what your data says. And I would be more troubled. The thing about collinearity that bothers me more is if you have two variables that look exactly the same, then that tells me those aren't you're not measuring different things. And once you add in error, you're probably not measuring differences at all. So I would be concerned mostly for that. But when you get really high correlations and there's no separation between two variables, that can cause instability in your models. Because maximum likelihood can have a hard time settling on a best choice. All right. So the second thing is influence. So certain variables, particularly when you have small data sets, can have a large, unduly large effect on the outcome. And so one thing is to pay attention to the residuals. If you have variables, if you have certain observations that have very high residuals, you should probably pay attention to that. And there's a variety of models I've done over the years where I just try to get rid of those. So I was estimating, for example, one time using a very complicated multi-level model, I was trying to estimate the price of heroin in a whole bunch of communities. And sometimes, the police say that they bought their heroin for an outrageous price, but it was really bunk heroin. And so if you look at price per unit pure, it looks like you're paying just an outrageous price, and I just don't want those kind of influence. I just don't want those variables as bad data. So sometimes you're filtering through your data and you're looking for bad data. Sometimes things are just different, and you might have a problem with the unit or something like that. So we'll talk about that in a second. Collinearity, it's simple to check. Here's just a correlation between market condition and years. You can see that they're not particularly related. So these variables I wouldn't worry at all about. You can use a graph to look at it as well. So pretty standard, easy technique for checking that. Influence can be checked by looking at the residuals. So here I calculated the standardized residuals. You can see that there are certain variables that stand out. These are standard deviation units. Statistical significance is right here at the second standard deviation. So all of this would be not statistically different based on the two standard deviation unit standard. But once you get up to 3, whoa, those are really large. Those have a large effect. So if you look here, Mississippi, Florida, and DC tend to have very large residuals, suggesting that the model doesn't work particularly well. And you can see that here, that DC is really an outlier, as is Mississippi. When you look at the regression line and you plot the regression line versus the data. So this is data predicting crime based on a whole bunch of stuff. I don't want to go into the model here, but suffice it to say, DC, if you think about this line as having a fulcrum, right? So if you think about the middle, right, in a seesaw, right, this DC is pulling up on this line pretty heavily, whereas Florida is pulling up on the line down here. And so that, in some ways, they counterbalance each other, but I would be particularly worried about DC because it's at such an extreme value of X that it's going to have a lot of influence on it. And in fact, we can see that if we run the regression that includes both DC and not DC. So here I've included DC, and here I said if state isn't equal to DC. So you'll notice there's 51 observations here, and there's only 50 observations here. So I've got rid of one of the observations. Now, when I look through differences between these coefficients, what really stands out for me is single parent. So with DC, the percentage of single parents is a very strong predictor of crime. When I get rid of DC, the percentage of the population that is a single parent is much lower in crime, has a much lower effect on crime. So it seems like a lot of the relationship between single parenthood and crime is being driven by DC. And that's because DC is a city with particular urban stuff and everything else here is a state. And so I would say that DC is probably not something good to model. I would probably exclude DC in this context, but that's a judgment call, and you can make your judgment calls. I think you just have to be able to defend it honestly when you present it to your colleagues. There's a whole bunch of other regression assumptions, and we're going to spend a lot of time talking about some of them. So the first one is additivity and linearity. We have made assumptions through most of the models that we've run that there is a linear relationship between our X and our Y variables. We loosened that up a little bit when we created an interaction between male and years of experience. So we added a multiplicative function. We're going to do that a lot in this class with time in particular. We're going to look at quadratics with time. Those are interaction effects that make assumptions of, that loosen the assumption of additivity. And there's a few other ways that we're going to be able to do that as well. But we're really assuming that there's a strong linear relationship between almost all of our variables. And that is probably the strongest, most dangerous assumption that we make, and not one that we always check. We also assume normality of errors, that our errors are normally distributed. You saw that in the formulas earlier. We can test for that. I'll show you some tests in a second for that. It's one that people like to pay attention to. It's not really the most important. Our modern techniques deal with it pretty well. Robust standard errors adjust for most of the problem associated with that, and homoscedasticity, which is another problem. So we can do transformation. So we have a variety of tools at our disposal to deal with non-normality. Again, it's the normality of the errors, not the independent or the dependent variable. It's not the Y variable that has to be normally distributed. It's the errors that have to be normally distributed. So it's the what remains of the Y variables after accounting for the X variables. All right. So we assume that our coefficients, we assume that our errors are identically and independently distributed, meaning they're substitutes for one another. This assumption right here is the one that we are going to is going to be violated in our data, and that's why we're going to use the techniques that we're going to use. Our data are going to have relationships. So, for example, if I have a data set that includes siblings, those siblings are going to have a relationship. I am screwing up my children in my own particular way. If you have children, you're screwing up your children in your own particular way. And those ways affect both of your children, making them not substitutes for one another. You can't just switch them in and out because they live in some normally distributed population. They have a relationship between one another, and we have to account for that relationship. The strongest one that we generally deal with is when you measure yourself at multiple observations. I am more related to me at time 2 and time 3 and time 4 and time 5 than you are to me at any time, right? So, in general, there's a very strong within-person relationship. And if we don't account for that, then we have really shrunken standard errors. And so almost all of the techniques we're going to deal with is an approach to deal with this error, to deal with this assumption and allow our data to violate that assumption. In fact, love that our data violates that assumption. Use that information. We've talked about homoscedasticity. We'll talk about that in a second as well. We assume that observations are independent of one another. I just described that earlier. We assume that errors that variables are measured without error. This is the biggest problem that we do not discuss in this class. There's a little bit where we might discuss a little bit of it. You can deal with it in SEM. There's some Bayesian techniques that allow you to deal with it. But we really, so if we were to include the CESD measure of depression in our data, we would just include the score that somebody got. Well, that score has a tremendous amount of error associated with it. I guarantee you there's a lot of error in any of the psychometric measures that you're using, but we don't include those in our models. We assume that these are measured without error, and that's a huge problem because all of that bias is baked into your variable. Fortunately, if you want to be conservative, it's a conservative bias in that it makes our variables more noisy, right? So if we're throwing in random error, or even systematic error, but random error, what we're really throwing in is a bunch of noise. So it's harder to detect the signal in it. So it makes it harder to get statistically significant findings. So that's a conservative bias. That's good. On the other hand, we sometimes want to know whether a service that we're providing works. And if we can't detect that because we've done a poor job measuring, then we're failing at our task. And then model validity. We talked about data generating process. Are we doing a good job? Are we choosing the right variables? Do we have all of the relevant variables? What variables are we missing? And are they essential to understanding the relationship of the variables we do have and the dependent variable? Is our model based in reality or is it nonsense? And we can talk a lot about that. But this is a conceptual issue that there's no statistical answer to. But there are some statistical answers to a few of these problems, and let's just run through them quickly. Residual diagnostics. So here's the salary model that we've been working with a lot today, and we have our structural component here, which is all of the variables, male, market, years of experience, and the interaction between male and market. And we've taken the variance attributable to the grand mean and all of these differences, and we put that into the model variance bucket. But there's a remaining residual. Here I've termed it an error because I'm in the theoretical space, but in the practical space, it's a residual, right? So if I take the actual salary, subtract it from the value that I get from this, that gives me my residual, right? So generally we talk about this as y hat sub I, and this would be y sub I, right? So you've seen this is how you calculate residuals in the past. Now this is where we make the assumption that conditioned on all of the x's, that this term is normally distributed with a variance, a single variance term, right? So we can calculate the residuals. We'll never see the error term because that's a theoretical term because we never quite know these betas. We've just estimated the betas based on our data. But so we're dealing with the residuals, and we can look at the residuals. You've done all of this before. We can look at kernel density plots and their relationship to normality. We can see here using Shapiro-Wilk that there's some deviations from this is a QQ plot. I'm sorry. You can see in the QQ plot that there's some deviations from normality. Normality is the line. If it's all in the line, that's normal. The Shapiro-Wilk test down here tells us whether normality is a good assumption. This high p-value tells me that it's not a good assumption. So there's something off about my variables. About my residuals. If I look at the residuals, so the residuals are on the y-axis, the fitted values are on the x-axis, and this is a really good plot to look at in general, and we'll talk about how to do that. You can see the shape of the data. That is heteroscedasticity, right? We want these all to be within a certain bound, right? The fact that there's a much narrower range of variability at this level of the dependent variable and a much higher range of variability at this end, which is not surprising given the data and the plot that we looked at. When we looked at the histogram at the beginning of this discussion, I mentioned that there's a much larger tail out for the higher salary range. That's what we're seeing. We're seeing the consequence of that here. Our model has not done as good a job of capturing the variability at the high end. And so we have a problem to deal with. There's a variety of different techniques that we can use to deal with it. Robust standard errors should always be used, and that solves for this. But we can also transform the data. And one traditional way of dealing with this in dollar terms and salaries, and if you read an economist, they never talk about dollars. They always talk about log dollars. I personally have no idea what a log dollar is. The log scale is very confusing, but here we logged it, and you can see, not surprisingly, you still see a little bit of it, but it's now it's much better, and our Shapiro-Wilk test looks great, so we don't have to worry about it as much. Again, this is not the biggest form of worry for me. A lot of the other things, the more conceptual issues, the measurement issues, and then the non-independence of observations, which we are going to spend most of the rest of the class on. So thank you for this. I look forward to seeing you in the Zoom sessions, and we can go over this, answer some questions, look at this data, and hopefully make it a little bit more understandable. All right? Take care.